Well, I guess that's the last talk. It's going to be about quantum mechanics. So, of course, this is dedicated to the memory of Christoph. Here you see a few pictures. Probably you saw most of them, except the one at the bottom to the right. That's a picture from Rome a few years ago, and there was a meeting at the Accademia dei Lincei, and we had a good time there. So here are a few things about my encounters with Christoph. I think we first met in 1978. The 76 is wrong. It was the Carget School was in 79. So we met in 78 at Carpatch, and then I invited him to visit IHES in 1981. And during his stay at IHES, the General Jaruzelski declared martial law in Poland. And then, of course, there was a debate whether Christoph should stay in France. His family was still back in Poland, but in the end, he decided he would stay. And I think it is really thanks to Louis Michel that very soon after the decision, Christoph got the CNRS position, which offered him some stability. So, well, maybe that's a story I wanted to briefly tell you. I have one joint paper. He became a sort of steady companion for me ever after, but we hardly ever collaborated. But we do have one joint paper about that is sort of a little bit non-commutative. I think it's neither his nor my best paper, but it was amusing to think about these things. We have, of course, we had many common interests and a lot of very heated debates. I confess that I found him sometimes a little intimidating, but it didn't undermine our strong feeling of friendship. So what about this lecture? I will tell you a few things about a new way of looking at quantum mechanics, and then I will mainly focus on examples that could already have been discussed in more or less in 1916 when Einstein introduced the A and B coefficients for the interaction of matter with light. My work goes back to more or less extends over the last 10 years with various collaborators. So here is a little summary. I present some ideas about how to extend the standard formalism of quantum mechanics in such a way that the theory actually makes sense. You know, most people use quantum mechanics, but when you ask them what does it actually mean, they get terribly confused. And I think it's time to get rid of these confusions. I call my version of talking about quantum mechanics ETH Approach, E for events, T for trees, and H for histories. This approach yields a new general law for the time evolution of states in quantum mechanics. Most of you think that, well, that's given by the Schrodinger Equation, but that's, of course, wrong. So I will give you the right version of evolving states in quantum mechanics. The goal of these studies is to try to get rid of the enormous confusion that is still around in the physics community about the deeper meaning of quantum mechanics, although the theory is soon going to be 100 years old. So I think we have to try hard to get rid of this confusion. Now, So an example of confusion. Look at the fluorescence of a single atom. So for example, you take a static atom in the superposition of two internal states, a ground state and an excited state, and you put it into a laser beam, then it starts to exhibit Rabi oscillations, but every once in a while it will spontaneously emit a photon. And this process of emission appears to be absolutely perfectly stochastic. So you cannot describe it with a deterministic equation such as the Schrodinger equation. There are papers in the literature, for example, Yves Beaumont and his collaborators, including Jean Ginibre, wrote papers where they just introduce an ad hoc theory of describing this process, which has very little to do with quantum mechanics. And of course, that bothers Beaumont, and then he appeals to Everett's many worlds interpretation of quantum mechanics to motivate what he did, which is basically meaningless, I think. So I believe I have a way of describing this process that is logically coherent, and that's sort of probably the main part of this lecture. So we have to address a few topics. This talk was called Past and Future in Quantum Mechanics. So I want to explain to you how quantum mechanics distinguishes between past and future. And of course, this goes back to antiquity. Aristotle distinguished potentialities from actualities. And quantum mechanics has a perfect way of making this distinction. I want to introduce a good notion of isolated physical systems. I'm not going to say very much about this. Then about events. That events are important notions in quantum mechanics was always emphasized by Rudolf Haag, and I think he was perfectly right about that. Then I want to briefly convince you of the inadequacy of the Schrodinger equation to evolve states in quantum mechanics. And the rest I won't touch upon today. So really, this is going to be about non-relativistic quantum mechanics. However, there is a relativistic version of the same ideas, which is a little more complicated. I first wanted to explain it today, but I think it's too much for a short talk. So instead, I will look at this example of the fluorescence of atoms. That will be the main part. So here about past and future, if you imagine that the universe evolved with a big bang after a period of inflation, then obviously an observer anywhere in the universe will not be able to predict the future. Why? Simply because he does not have perfect access to the initial conditions in the past light cone underneath him. And that means that, you know, there may be bombs that exploded somewhere outside my past light cone, which will enter this room in about 10 minutes and kill us all. That cannot be excluded. It's unlikely, but one cannot be sure. So the fundamental dichotomy of past and future is something that we should try to retain in quantum mechanics, and in fact, quantum mechanics does it perfectly. Let's go on. So this is about the inadequacy of the Schrodinger equation. Everybody knows that when you do a measurement or an observation, then apparently Schrodinger doesn't describe how the state changes. That's an old idea. But why should it describe how the state changes when nobody looks? There's absolutely no reason why that should be the case. So there are lots of Gedanken experiments. I think I have the best Gedanken experiment to show why the Schrodinger equation doesn't really work as an evolution equation for states, but it's a little too long to describe it. What is more commonly known is this Wigner's friend experiment. You have a lab. Inside this lab, there's a little lady who is a friend of Wigner's, and she does an experiment. She thinks that the experiment is successful, and she has perhaps not looked what the outcome is, but in any event, she will describe the future if she hasn't looked at the result with a density matrix that splits the possible outcomes of the experiment. However, Wigner is outside the lab, and he believes he can describe the lab and his friend inside and the experiment she does all with a unitary Schrodinger evolution. And then, of course, the two will make different predictions about the future, which is sort of perfectly obvious. But people get excited about this example. There must be about probably thousands of papers about it. I think it's sort of an obvious thing. Anyway, it's supposed to show to you that the Schrodinger equation is probably not the right thing to describe the evolution of states. So let's briefly explain how states evolve in quantum mechanics. So I consider a physical system. Physical quantities characteristic of the system are represented by certain abstract bounded self-adjoint operators, a list of such operators. This list has the property that if an operator x is inside the list, and you apply a bounded continuous function to x, then the result is still in the list, but otherwise the list has no structure. I will not think about how time emerges in physics. I just assume there is time, and I use it as one of the fundamental quantities to describe the evolution of a physical system, or to parameterize the evolution of a physical system. Now, at every time, there is a representation of the list of abstract self-adjoint operators by concrete operators, x of t, acting on a Hilbert space. These concrete operators can be localized in space and time. Haag talked of local observables, Bell of local beables, not a very elegant notion. In any event, an operator x representing a physical quantity x hat in my list is supposed to be localized in a compact interval denoted by I sub x of the time axis. Now, in the Heisenberg picture, we know how these concrete operators x of t representing abstract physical quantities evolve in time. Well, x of t prime at the time t prime is conjugated to x of t simply by the usual Heisenberg evolution that we all know. This is a perfectly deterministic evolution that just tells me how the concrete operators representing physical quantities change with time. All right, let's see. Oh, yes, I jumped, I guess. So, let I be an arbitrary interval of the time axis, then I introduce an algebra E sub I, which is generated by all concrete operators representing physical quantities that are localized in the interval I of the time axis. E greater or equal to t is the algebra generated by all E sub i's, where I is contained in the interval from t to infinity. And then, well, then you can put them together if you like and introduce an algebra E, but it's not so important. Obviously, just by definition, E sub I contains E sub I prime if I contains I prime, and E greater or equal to T contains or is equal to E greater or equal to T prime if T prime is larger than T. Now you have all been brainwashed in your courses to believe that these algebras E greater or equal to T are independent of T. Well, that turns out to be wrong in general. So I will tell you why in a little while from now. So now let's introduce a notion of potential events, of events that might happen in the future. So what is a potential event that happens at some time t or later in the future of the present time t naught? Well, it's given by a partition of unity in terms of disjoint orthogonal projections. So the pi sub xi's are projections, capital X is the spectrum of the event, and if you sum the pi sub xi's over all xi's in X, you get the identity. All right, so that's a potential event. Now we can define an isolated physical system in terms of a co-filtration of algebras E greater or equal to T, where T is time. And these are algebras of potential events. Now the principle of sometimes it's better to think about general concepts and general ideas rather than just sitting down and calculate. So here is a general idea, and that's this principle of diminishing potentialities. It tells us that the algebra E greater or equal to T prime, generated by all potential events that may happen at time T prime or later, is embedded and is properly embedded into the algebra E greater or equal to T whenever T prime, the time T prime, is later than the time T. So this principle characterizes what I like to call isolated open systems, namely systems that can release events of which I can take notice. For example, they can emit photons. So this principle can be shown, and I will briefly mention it, why it is true in a variety of situations. So what is a state? Well, naively we say a state is a density matrix on the Hilbert space H sub S of the system, and then the expectation of a physical quantity A in the state given by the density matrix capital omega is simply given by taking the trace of omega dot A. Now this notion of state is a misnomer because it doesn't tell me anything about how the system really, in what state the system is at some time t. Oops. So, what is a state in a more, correct way of the name? It is simply the restriction of a state in quotation marks to the algebra E greater or equal to T of all potential events that may happen at time t or later. This is actually, this notion of state is equivalent to saying that the state at time t is given by a quantum probability measure on the algebra E greater or equal to T in the sense of Gleason. I don't have to really insist on that. If you know what I mean, then it's good, and otherwise you haven't missed anything. So, in accordance with the Copenhagen interpretation of quantum mechanics, it appears very natural to say that the potential future event actually happens at some time in the interval t to infinity if the state at time t can be represented as a convex combination of states that correspond to individual projections pi sub psi that make up the potential event of which I'm talking. So in other words, there should be no off-diagonal elements. The state at time t should be a mixture of states that correspond to individual outcomes of the event. So this should be clarified because these algebras E greater or equal to T usually don't admit any pure states, meaning that in some sense every state is mixed. However, there is a better notion of what you mean by a mixed state. I think I should skip it. It's an easy notion that involves looking at the centralizer of the algebra E greater or equal to T and then passing to the center of the centralizer. But I don't think we have to go through that. It's the last talk. You're probably tired. And so let's go on. So, let's see. Yes. So, here is a definition. Given that omega sub t is the state of a system S at time t, an actual event is setting in at time t, if the state omega t can be viewed as a mixture of labeled by the projections that describe this event, okay? And there should be at least two projections in the event that both have positive, strictly positive bond probability and that are orthogonal to one another. Okay. So it's easy to see that if an event if an actual event happens in the sense of this definition, then really the state omega sub t is such a mixture. In other words, the equation we had on the previous slide, this equation 5, then holds. So now we should try to understand how these notions enable us to describe the time evolution of states in quantum mechanics. And this is based on introducing a certain state reduction postulate that I will explain next. So let omega t be the state of the system at time t. Let dt denote the time step. I will assume for the moment that dt is not an infinitesimal quantity, it's a positive quantity. I go forward in time by a little bit of time. Okay. So omega bar at time t plus dt is the restriction of the state of the system at time t to the algebra of potential events happening at times t plus dt or later. Here is an axiom, and this axiom describes the time evolution of states in quantum mechanics. So let's assume that f sub t plus dt is the partition of unity that generates the spectrum of the actual event that happens at time t plus dt in the sense of the definition I just gave on the last slide. Then nature replaces the state omega bar t plus dt by a state that is obtained from omega bar by projecting it onto the range of one of the projections pi sub psi that make up the event happening at time t plus dt. And of course, the projection to be projected upon should have a positive bond probability. The probability to select the state omega sub t plus dt psi is simply given by the bond probability of the projection pi sub psi in the state omega bar sub t plus dt. So that's an axiom. In other words, apparently states in quantum mechanics evolve according to a certain branching process. At every time there is some branching. And the law, the probabilistic law that describes the branching is given by this axiom CP, CP for collapse postulate. All right, so you see, here is a metaphor for how time evolution functions in quantum mechanics. You have events, they are represented by these red bullets, and then when an event happens, you have a choice to continue into the future. The choices are given by these projections pi sub psi. Nature chooses one of these directions to move into the future with a probability given by the bond probability of the projection, and the actual evolution of nature is given by a sequence, by a history, namely a path on this tree-like structure. So that's really what describes time evolution in quantum mechanics in the presence of this principle of diminishing potentialities, namely it only, of course, only something interesting that deviates from Schrodinger happens if these algebras E greater or equal to T are properly embedded into one another. Now, why should it be possible that these algebras are properly embedded into one another? This is in a theory with massless modes, such as photons and gravitons. This can be derived as a consequence of Huygens principle. You see what happens if maybe I should be a little brief and skip this and just show the picture. You see, here you have a picture of light cones. Suppose you stand at some vertex. So, suppose you stand at the tip of this green light cone, and and you look at the future, the E greater equal to T is described by all fields with supported inside the green light cone. If you go a little step into the future so that you get the red light cone, then it turns out for example, all electromagnetic fields in this double diamond that is contained in the green light cone, but underneath the red light cone, commute with all fields inside the red light cone. That's Heisenberg's principle. And therefore, in fact, the algebra of all fields localized in the red light cone is strictly smaller than the algebra of all fields in the green light cone. Is this better? Okay. All right, thank you. So that's Heisenberg's principle, and it shows that in the presence of massless modes, such as photons or gravitons, this principle of diminishing potentialities ought to work. I will actually look at the limiting situation when you let the speed of light tend to infinity, then these light cones unfold to time slices, and the algebras associated with different time slices are simply commute with one another. I think people now call of a clock degree of freedom to describe this limit when c tends to infinity. Of course, we don't really want to describe clocks in quantum mechanics, but anyway, it's an interesting limit to consider. It's a limit which will often be perfectly adequate to describe.
Please stand by the microphone here.
Yes, or you don't hear me anymore. I thought I had a very strong voice, but maybe not. Okay, so I stay here. So it is often very adequate to consider the limit when c tends to infinity to describe, simple systems of physics. And that's what I want to do in the last 15 minutes of this talk. So, I think I will spare you the exercise of verifying the principle of diminishing potentialities. I have here in mind a model of an atom with internal states which can interact with the quantized electromagnetic field, and I regularize the model in such a way that it makes sense by discretizing time. Time will proceed in steps of length 1. And then you can immediately verify this principle of diminishing potentialities and apply all the general ideas of the ETH approach to describe the time evolution of states for this particular model. I think this is, a setting that should interest mathematicians. This is a new kind of stochastic process. I would like to call it a stochastic process with a non-commutative state space, because the state space consists of events, but events happening at different times are described by projection operators that don't commute with one another. So it's really a new kind of, stochastic process that unfortunately mathematicians have overlooked so far. They should turn their attention to it. I think this will become an interesting endeavor. Now, since the generalities, even of this simple model of an atom describing, interacting with the electromagnetic field, since the details are relatively lengthy, I look at the simplified model that arises when the speed of light tends to infinity. And that's sort of the last part of my talk, and perhaps in some sense the most interesting part. So, I consider a very simple atom with just 2 levels. And I will describe the 2 states, the ground state and the excited state, as spin down and spin up. The Hilbert space of these internal states is simply C2. There are 2 experimental setups that we may consider. Well, I couple this atom to the electromagnetic field, and there are two possibilities. I can look at either one atom put into a laser field, and then it exhibits these Rabi oscillations and occasionally the spontaneous emission. Or I can look at the whole stream of atoms. I can look at an atom gun of the sort that, for example, appears in the Arrow-Schremont experiment. It spits out an atom, the gun spits out an atom every tau seconds. The atom then travels from the source to a detector where its internal state is measured. And along the way, from source to detector, the atom might emit a photon. Now, you can do two possible experiments. You're not interested whether the photon has been emitted or not. In other words, you don't detect photons in your experiment. That can be done. Or else you put the photomultiplier into around the path of the atom from source to detector, and as soon as the atom releases a photon, the photomultiplier will be hit and will click. It turns out that these two situations really, in these two situations, you predict different outstates for the atom, and I would like to explain that a little bit. So we describe states of the atom by these density matrices rho of n. N is a vector of length smaller or equal to 1 in 3 space, and rho sub n is 1/2. The identity 2x2 matrix plus n dot, the vector of Pauli matrices. The state is pure if n is a unit vector, then rho of n is a rank 1 orthogonal projection, and rho of n plus rho of minus n is the identity. And of course, if you take the trace of rho of the product of rho of n with the vector of Pauli matrices, then you recover the vector n. So if lambda is smaller than 1 and n is a unit vector, then the density matrix rho of lambda n has two eigenvalues, 1 plus lambda over 2 and 1 minus lambda over 2. The eigenspaces are given by rho of plus or minus n. Now I introduce a Hamiltonian for the atom in the absence of the electromagnetic field. It is simply given by 1/2 omega dot sigma. Omega is the vector 0, 0, capital omega. It stands in the z direction. Omega is a circular frequency. And then, of course, if you evolve the state of the atom by the Liouville equation from time 0 to time t, then the unit vector n sub 0 that you had at the beginning turns, becomes a unit vector n of t, given by, in polar coordinates by the usual formula, and the polar angle phi of t is phi naught plus omega dot t. How do we now define the pure states of the electromagnetic field? Well, we describe them by unit rays in the Fock space. 0 in parentheses is the Fock vacuum, and projection onto the Fock vacuum is denoted by P naught. Gamma is some state with at least one photon that may arise because the atom spontaneously emits some photon, and the projection onto this state gamma is denoted by P sub gamma. Obviously, the two states are orthogonal. The trace of P naught times P gamma vanishes. The explicit time evolution is not needed for my discussion. Of course, it's of interest, but I won't look at it. In any event, I will describe the photons in the limit where their speed of propagation tends to infinity. The states of the photomultiplier that may be present in order to detect photons will not appear explicitly in my discussion, so I will not talk about them. The only important feature is that the state of the dormant photomultiplier is orthogonal to all its states after it is hit, right after it is hit by a photon. When it is hit by a photon, eventually it will relax back to the dormant state by a process of dissipation, which works very well if the photon multiplier has infinitely many degrees of freedom. So we assume that the interaction between the atom and the radiation field is weak, as measured by something like the fine structure constant alpha, which I assume is much smaller than 1. Now I want to look at the effective time evolution of an atom coupled to the radiation field, and I first consider the situation where there is no photon multiplier that detects emitted photons. So when we pass to the limit where the speed of light tends to infinity, and if we start from a state for the radiation field that does not correlate modes at different times, then the effective time evolution of the atom after tracing out the radiation field is actually naively described by a Limblad equation, but let's describe it as follows. The analog of the state that I introduced previously, namely this omega bar of t plus dt, this state can be described by a vector m bar of t plus dt, which is given by the unit vector that describes the pure state of the atom at time t, plus a dnt. And dnt satisfies some kind of stochastic differential equation. And the only important fact that we should keep in mind is that the vector m bar at time t plus dt tends to be a little shorter than 1. It's 1 minus order alpha times dt. dt is the length of the time step. And that is strictly smaller than 1, except if n of t is E3, then in fact the state of the atom, if it is in the ground state, it will not change when it travels from the source to the atom detector. But as soon as it is somewhat excited, the vector m bar of t plus dt tends to shrink a little bit during the time evolution. And now, what are now the events that may happen? Doesn't seem to work anymore. Doesn't transport. Can anybody shift the transparency? I think this maybe the battery is low. No, but is there anybody at the booth? No, okay. So you see, the axiom I introduced when I reviewed the ETH approach, this axiom that describes the state reductions that happen when events happen, this axiom in the present example gives rise to a Poisson jump process, namely the vector describing the state of the atom at time t is mapped to a unit vector describing a pure state of the atom at time t plus dt, which is given by the vector n bar at time t plus dt normalized to the length 1, and that happens with probability 1 minus order alpha times dt. However, with a probability order alpha times dt, the vector n of t gets mapped to a vector n of t plus dt, which is just the antipode of the vector I described before. So you can see the different sign here. So the rate of this jump process is proportional to the fine structure constant alpha. In other words, there tends to be roughly one jump from n of t to the antipode of n bar of t plus dt every order alpha inverse times tau seconds. So when entering the atom detector, the state of the atom is is actually given by a certain incoherent superposition of two things, namely it's either given by a state rho of n out. N out is can be described by the polar angles theta prime, phi out, etc. Theta prime is either close to the initial angle theta naught whenever there is no jump, or it is close to theta naught minus pi when there is one jump, when the atom releases a photon. So that's what comes out. But basically, with high probability, the angle theta prime hardly changes when the atom travels from the source to the sink. However, if you install a photomultiplier, things change. Namely, in that case, you know, the detector also has to be described quantum mechanically, and the quantum mechanics of the entire system can now be described as an effective evolution of the atom coupled to the radiation field, and the outstate of atom plus radiation field is either a rho of n out tensored with the projection onto the vacuum. That happens with a probability of given by 1 minus order alpha. This happens if no photon has been emitted and therefore the photomultiplier didn't click. But with a probability of order alpha, the outstate of the atom is given by rho of minus E3. The atom is really in the ground state, tensored with a state that describes one or several photons. This is very different from the outstate that we had before, because before the outstate, you know, the ground state didn't play a special role for processes that happen in the absence of a photomultiplier. So the difference between the outstate of the atom in the presence of a photomultiplier and in the absence of the photomultiplier can in principle be discovered in experiments, I think. This is, you know, I tend to think that I may be the first person in the universe who has come up with a correct quantum mechanical description of this process. If you look at the literature, it's all confused. But this is very clear. If you apply the rules of the ETH approach, you get a perfectly clear dynamics, stochastic dynamics for this system with results that I sketched here. So I think it's time to stop. Summary and conclusion. The ETH approach to quantum mechanics provides a logically coherent description of the time evolution of states in quantum mechanics, which supersedes the Schrodinger evolution. And it describes the ontology of the quantum theory is described in terms of events and their recordings. Of course, this has some, since there is a stochastic branching process involved, you may be reminded of the many worlds interpretation of quantum mechanics, but I only describe one world, namely ours, and the branching rules of the branching process are perfectly clear and unambiguous, very much in contrast to the Everett formalism. As in the genesis of special relativity, fields describing massless modes, photons and gravitons, play a special role because it is thanks to the existence of such modes that the principle of diminishing potentialities can actually be verified. In a theory where all fields are massive, the principle of diminishing potentialities fails. So, thanks to this principle, there is a perfect, distinction between past and future in quantum mechanics, and furthermore, I believe that this enormous debate about the information and the unitarity paradoxes in the presence of black holes will just completely disappear. It's all based on misunderstandings that the Schrodinger evolution should describe evolution of states in quantum theory, which is simply not the case. So this is my last slide. I think many of us have been very privileged with a wonderful past. Of course, this past is filled with encounters with Christoph. Here you see another picture of him when we were in Rome, having a good time. And unfortunately, I have to say I'm very pessimistic about the future. What you see here on the right is a painting from the Cathedral of Segovia in Spain. And you know, I'm reminded of our situation when I look at this wonderful painting. So thank you for your attention. So, so the answer is very short and simple. If you're willing to consider models in the limit where the speed of light tends to infinity, then you can pass to zero time step, because these models make mathematical sense. If you want to remain fully relativistic, which has many big advantages, then unfortunately, since we don't know, the ultraviolet limit of theories in 4 dimensions to be well defined, it is very tempting to introduce a finite time step, because that introduces an ultraviolet regularization. And then, in fact, you can verify the principle of diminishing potentialities, but at the price of having a finite time step. But if you are happy to work with models in the limiting regime where the speed of light tends to infinity, you can let dt tend to 0.
Okay, so that's a very good answer, but it shows that we don't understand the relativistic version of the
Well, look, what do people do if they cannot introduce models that they can fully discuss? They introduce an axiomatic framework. And there is a wonderful axiomatic framework that describes this version of quantum theory in the relativistic case, which in fact I thought I should present here, but it turned out it was just too much material to be presented in 45 minutes, so I decided against it. But there is a nice axiomatic framework that describes the ETH approach in a fully relativistic setting. Then whether there are models or not, is a question of whether we understand quantum gravity or things like that, and of course I don't understand it.
Concerning the general framework, what can you say about the classical or semi-classical limit?
You want?
I mean, the general setting of the ETH approach. How is classical theory incorporated in?
Oh, well, I could have. This year I gave many talks about the problem of understanding why particles leave tracks when entering a detector. For example, Vincent heard it in Oberwolfach, and I also gave the same talk elsewhere. So the appearance of tracks of particles when they travel, for example, when they scatter, when you do light scattering, or when you let them enter a bubble chamber, the appearance of tracks is really an exercise in passing to a semi-classical regime. with this formalism, and you know, there is no problem of doing that. But it's another talk. I cannot give this talk now. It would take another 45 minutes. Well, if there are no further questions, I fear that probably not many people understood what I wanted to say, but I hope you enjoyed it anyway, and you can read my papers.